It's my pleasure to present today Dr. Kaoutar El Maghraoui. In fact, we are very happy to have you with us today for your talk entitled Powering the Future of AI Through Specialized AI Hardware Accelerators. Dr. Kaoutar El Maghraoui is a principal research scientist at the IBM TG Watson Research Center, where she is focusing on innovations at the intersection of systems and artificial intelligence. She leads the research agenda of end-use experimental AI testbed of the IBM Research AI Hardware Center, a global research hub focusing on enabling next-generation accelerators and systems for AI workloads. She co-led IBM's Global Technology Outlook in 2017, where she contributed to creating IBM's vision for the future of IT across global labs and business units, focusing on IBM's AI leadership. Dr. Kaoutar has co-authored several patents, conference, and journal publications in the areas of systems research, distributed systems, high-performance computing, and AI. Dr. El Maghraoui holds a PhD degree from Rensselaer Polytechnic Institute in USA. She received several awards, including the Robert McNaughton Award for Best Thesis in Computer Science, Best of IBM Award in 2021, IBM's Eminence and Excellence Award for Leadership in Increasing Women's Presence in Science and Technology, and several IBM Outstanding Technical Accomplishments, and 2021 IEEE TC-SVC Women in Service Computing Award. Dr. Kaoutar is Global Vice Chair of the Arab Women in Computing Organization and a avid supporter and active member in many Women in Science and Technology initiatives. Thank you, Dr. Kaoutar. And please, the floor is yours.
Thank you so much, Iman, for the generous introduction. It is really my great pleasure and honor to be here today with all of you, especially as we're almost about to close the conference. So I hope you've had a wonderful conference. I myself enjoyed it very much. So my name is Kaoutar El Maghraoui. My background from my PhD days were distributed systems and high performance computing. But along my career, I have kind of converged, like many of us, to the area of artificial intelligence. And currently, my current research interests are in efficient deep learning techniques with a focus on AI automation across the life cycle of AI applications. I'm part of the IBM Research AI Hardware Center, leading our testbed infrastructure efforts and working closely with our partners. And in this talk, I'm going to talk about what we're doing at IBM Research, but also some of the key trends happening around enabling efficient AI and also green and sustainable AI. And my talk is about how do we power the future of AI through specialized AI hardware accelerators. So first, I would like just to start by giving a quick introduction about IBM Research. IBM Research is the world's largest and most influential corporate research lab with an unmatched investment in basic research and core science, and commitment also to invent the future of technology by making scientific breakthroughs that will transform industries and society. We're more than 3,000 creative, scientific, and technical minds worldwide, and lots, a tremendous track record in terms of innovations and also contributions to science and technology, with the 6 Nobel laureates, 10 national medals of technology, 5 national medals of science, 6 Turing Award winners, and 26 consecutive years as the #1 patent producer. IBM Research also is a global research capability that spans many labs worldwide, and the activities of our global labs reflect both local and market needs and the deep technical expertise found in these key regions of the world. You can see here our labs, span many continents. The African continent, we're present there in Africa. We have, a lab in Kenya. We also have a lab in South Africa. I'm hoping soon we'll have a lab in Morocco. We also have labs in Europe and the India, China, Tokyo, and of course in the US, 3 labs in the US. So, for example, in Africa, we're developing commercially viable solutions to transform lives and spark new business opportunities in key areas such as agriculture, healthcare, financial inclusion, energy, blockchain, and cloud computing. And in India, for example, we're bringing cognitive technologies to bear in solving problems with several industry domains such as financial services, education, human resources, and even fashion. IBM also research collaborates across many disciplines to address some of the world's most complex problems and promising opportunities. And we actually strongly believe that profound breakthroughs will come when businesses, governments, academic institutions, and others work together to tap into diverse points of views and expertise. So you see here some of the areas that we're looking at in research that span from cloud computing, AI, quantum, semiconductor and systems, security, physical sciences, mathematical sciences, life sciences, and of course, computer science. And one thing I would like to point out that IBM has had a long history of innovations in AI. Of course, as you all know, AI is not a new field. AI has its roots, many years, many decades ago, but it just until, very recently with the revolution that deep learning has created that we see this explosion of interest across many domains, many modalities in industry, academia, and so on, where we started reaping the benefits of artificial intelligence. So, for instance, in 1957, this was actually the first working chess program. And the TD Gammon, which is a computer backgammon program developed in 1992 by Gerald Tussaro at IBM's Thomas J. Research Center. Its name comes from the fact that it is an artificial neural network trained by a form of temporal difference learning, specifically TD lambda. And TD Gammon achieved the level of play just slightly below that of the top human backgammon players at that time. It was really kind of a breakthrough at that time. It explored strategies that humans had not pursued and led to advances in the theory of correct backgammon play. And these are where some of the foundational things for AI. Another thing also, these are this was the first demonstration of a neural network and reinforcement learning in the complex domain, the TD Gammon. Also, the first computer to defeat the world chess champion, which was the Deep Blue computer in 1997. That was also another breakthrough and a big advancement also in the AI field. And more recently, we also built the first computer to defeat the best human in the Jeopardy game using the Watson technology, and significant contributions in the area of question answering. And very recently, also the first computer to debate humans convincingly through the Project Debater. These are just some of the key landmarks that we have in the history of IBM's research contribution to AI, and there are many, many others. So coming to today's topic, if you look at AI, and especially if you want to do AI at scale, it really requires advances across the stack. You cannot just focus on one stack. You have to look at innovations going all the way down to the silicon, to the wire, to the devices, to the materials that you're using to build hardware to run these AI models. And this is really needed to handle the probabilistic nature and also the huge computational demands that are needed to do today's AIs and also the future AI models. So what are the trends that we see here and why there is this tremendous need for efficient deep learning? AI and especially deep learning, as we all know, they have achieved incredible performance in numerous fields, including computer vision, speech recognition, natural language processing, etc. However, with this huge success also comes increased complexity. The first thing that here we're noticing is there is this increase in model complexity, and it's just, we've noticed this trend. These deep learning models, they're just getting larger and larger and also deeper with millions, billions, and recently we have trillions of parameters. And in fact, the number of the parameters in deep learning models is increasing in the order of 10x year on year. This is really huge. So you can see here the trends. Just very recently, the there is a new model from Google, which is the switch transformer, which kind of marked, the 1.6 trillion parameters. So this year, this couple of models have been published that are much larger than what we've ever seen before, breaking this trillion parameter threshold for the first time. So this is the switch transformer that was published in January of 2021 by Google. And before that, we've also seen models like GPT-3, especially the language models. If you see here the graph on the bottom right, you see the trend here in natural language model progression, and it's kind of an exponential increase in the number of parameters these models, and the number of parameters basically, it's just the size of the model. So these numbers, and also this also is accompanied by this increase of data volume, sources, and the richness of AI models. The next thing is the increased size of complexity of these deep learning models. It doesn't come, without a cost. It also translates into high computational demands. In fact, compute requirements of large AI training jobs have been doubling every 3.5 months. And additionally, most of these models are too expensive to computationally, run on devices like cell phones or embedded devices or edge devices in general. You can see here, we're talking about exaflops of computing. Most of these models, they require huge amounts of computation. If you look at the graph here on the bottom, we're really looking at the number of petaflops. We're talking about 10 to the power 15 here, per sequence, per iteration for these models. And you see how this increases kind of exponentially here as the size of these models, are increasing. And we're kind of, seeing the range of sizes that we've started to see in very recently, especially as we see large, deep learning models applied, bring a lot of, interesting results in areas like natural language processing. The other thing here that we also notice is with this increase in computational needs, this also translates into increased carbon footprint and very high costs. Researchers at the University of Massachusetts at Amherst released in 2019 a startling report estimating that the amount of power required to train and search a certain neural network architecture involves the emission of roughly 626,000 pounds of carbon dioxide. This is really huge. And that is equivalent to nearly 5 times the lifetime emissions of the average US car, including its manufacturing. If we keep going at this rate, we're kind of going to consume the energy of the entire world just to train AI models. So this is not sustainable. And look at this example here, like for GPT-3 language model, which had 175 billion parameters. This requires 310,000 exaflop for training, which consumes 552.1 tons of carbon dioxide equivalent, which is about like 3 jets round trip from New York to San Francisco. So we're seeing this huge demand, computational demand, which also puts lots of stresses on our energy footprint. It has huge energy footprint. The data centers of today, especially with AI, they're consuming a lot of energy, and this is a problem that we have to solve. And there is so much work right now and so many efforts focused on how do we address this compute problem that we have with AI, and how do we address these increasing energy demands. And if we look also, there's also increased the rise of edge intelligence. And as the future of AI is moving to the edge and AI is becoming increasingly important at the edge, we need to consider more seriously a shift from state-of-the-art model accuracy to state-of-the-art model efficiency. Right now, a lot of the research is focused on how do I get AI models that get the best, model accuracy. But at the same time, we have to be also very conscious of how do we get AI models that also run efficiently in target platform when we deploy them. So learning at the edge, especially with reinforcement learning, will play a key role in the future. And edge intelligence comes with various challenges, such as resource-constrained devices. These are devices that are constrained, with in terms of CPU, memory, power, etc. And the difficulty also of deploying these models on a fleet of devices. There's also the instability of the network connection, and sometimes, these connectivity is not guaranteed or is not stable, which cannot, the data sometimes also due to privacy concerns cannot leave the devices in many cases. So edge intelligence comes with so many challenges, but so how do we address this given the fact that these AI models are also increasing in terms of size, they're requiring more energy, they're requiring more powerful compute. If we look at inference at the edge, which is kind of the dominant thing that we see here, and also there is an increasing trend, energy efficiency becomes very important. And deep learning applications in the small edge especially must meet a number of constraints: low latency, low power consumption, within the cost constraint of the small device. The necessity is optimized. This necessitates, to optimize architectures and microarchitectures with really optimized precision. You can see here some examples. For example, when you are in an IoT domain, this is some of the constraints. You cannot have more than, this is the energy, 100 milliwatts, less than few 10 gigaops that you can afford here. And the area also becomes important, less than few millimeters square. So you can maybe have one single AI core or chip here. Accuracy here maybe can be, the lower accuracy can be permissible. In mobile fields, so you can see here the energy requirements are slightly bigger, but you can also afford to do more, more computations, and you can maybe have not just one single AI accelerator chip, but few AI cores or AI chips. And the accuracy here is important. In the automotive field, here there are also lots of constraints, like 20 to 50 here watts, but and here sometimes you need more than one AI chip or core. But in this case, you cannot afford to lose accuracy. So there are really, for inference, varying requirements across different domains. Sometimes it's okay if I can get maybe some drop in the model accuracy, but in certain applications, it's not permissible because that's going to imply, people's losing lives if the car, fails at detecting that there is an object in front of the car while driving, or a person, or something that, could really cause some big damage. So these are just example varying constraints at the edge, and especially looking at the constraints in terms of the energy efficiency. And in this domain here, talking about TOPS per watt or teraops per watt becomes the key metric here. How many operations you can use per unit energy. So today, it is still so broadly inefficient the way we train deep learning networks with existing hardware, with GPU architectures, for example. And this gave rise to the need of these specialized AI hardware accelerators that are purpose-built to deploy deep learning applications efficiently, especially in real-time and edge devices, where there is a need to accelerate deep learning computations to achieve low latency, less than 20 milliseconds, for example, and even ultra low latency, 1 to 10 milliseconds, while also keeping the energy efficiency high. So it's really pretty clear that AI is the next big thing that is scaling and driving also a lot of innovations in the semiconductor industries, the companies that are building hardware to train these AI models or to do inference of these AI models. And we see the trends here. We're seeing that there is this move to specialize AI ASICs, or what we call application-specific integrated circuits. They're on the rise, and there is no one size fits all. So feature requirements are different in different use cases, and hence different choices of AI chip architectures. and the optimal compute architecture for AI will vary by application use case and hardware deployment scenarios. So deploying, developing or deploying these deep learning models is a bit like being a software engineer or a software developer 40 years ago. Right now, there are so many abstractions, high-level abstractions. When you're doing software development, like for example, if you're programming with Python, it's so high level that you really have no idea about the underlying pure architecture. You're not programming really closer to the operating system, the computer architecture. So you really don't have that deep, when you're programming, you have no clue, do I need to be conscious of the memories, footprint, or the registers, and so on. But 40 years ago, that was not the case when we were programming with things like Fortran or C or C++, when you also had to know to optimize your program for memory access and pointers and so on. So deep learning now is becoming like that. You have to worry about the hardware. And the hardware is also changing quite rapidly. So being at the forefront of deep learning also involves being at the forefront of what hardware can do. And this is a quote, from Phil Blanson from the Department of Computer Science at Oxford and also DeepMind. So what are we doing to address these challenges? In February of 2019, IBM launches a research collaboration center to drive building next generation AI hardware or next generation AI hardware accelerators. So, and IBM made a commitment to invest $2 billion, and also New York State committed about 300 million as well over the next 5 years. This generated a lot of interest in the technical community, and this is a very serious endeavor for IBM Research and the IBM company to build this ecosystem for enterprises and academic partners, and also to drive next generation AI hardware acceleration. So today, our center has 9 and growing members, and members, they include companies from materials companies, semiconductor equipment companies, major design automation companies, and also semiconductor chip design companies. We're growing and hoping also to have more members, especially in the end user space. So what is this AI Hardware Center all about and the mission here? So when we founded, this institution or this center, we believe that to address the opportunity for AI, and especially to help, move forward and address all these challenges around AI compute and the energy demands, we really need a full stack approach. You cannot solve these problems by just focusing as a single piece of the stack in the computational stack or the system stack. It is important to focus on the entire stack. And that's why when we build the center, we build it around these 4, what we call technical thrusts or technical areas. So the first one here is cores and architecture. And the goal here is to reinvent compute for deep learning and AI, focusing mainly but not exclusively on digital computes, using digital technology, and taking strong advantage for reduced precision, or what we call also approximate computations, to increase the compute efficiency. Moving to the right here, when precision is reduced enough, when we're talking about 2 bits, for example, instead of doing the 32 bits to do computations, analog computations become very feasible and become also important. So that's gonna take us to the next level of AI acceleration. So if your floating point precision requirement says 2 bits or 4 bits, then we start, we can start taking advantage of analog AI or using the physics of analog to do deep learning much more efficiently. And then, of course, when we're building these AI chips, you cannot build them in a vacuum. You have also to put them in a system and integrate them with other components. And then looking at all of these different things, the memory, the compute, the acceleration, the storage, the networking, you need to build a balanced system. So to scale this compute efficiency very high, it's really important to maintain system balance, like scaling the bandwidth, the connectivity, the memory capacity, And then otherwise, you're going to end up with a lot of unused silicon or unused capacity or less efficiency. And then the other thrust that we have here, which is the end user AI testbed, and this is the kind of, think of it as the software environment where we leverage and develop advanced AI software to take advantage of the new accelerators and capture emerging workloads needs. Excuse me. So the idea here is the center is hardware focused, but it is very important to show all of these hardware innovations in the context of key workloads and also study emerging workloads from the software perspective to see how these emerging AI workloads are also informing the design of our future hardware. So what I'm showing here in this chart is our roadmap for what's beyond the GPU or the graphical processing units for AI acceleration. What we've plotted in this graph here is existing and projected performance metrics of mostly GPU hardware that exists in the market today or has been announced by major players in the industry. So the question here, what technology do we need to develop to be able to maintain this rate of progress and go beyond the GPU? And how do we put another point here in this graph? So the first step is to build accelerators that exploit the fact that machine learning methods are highly tolerant to reduced precision computations. And the next advances will come from exploiting analog or in-memory computing technologies, which could potentially offer 100x in energy efficiencies. So let's look at what we're doing quickly in reduced precision computations, and then how do we get to the next level with analog computations? So building accelerators that exploit the fact that machine learning is highly tolerant to reduced precision is the key thing here for digital AI cores. And so let me first, explain what do we mean here by reduced precision. As you probably know, the transactional systems that we have built for many years and that have enabled things we now take for granted, like the modern economy, is built on the premise that 32-bit or 64-bit precisions are required. And in many cases, they truly are. If you're a bank and you deal with hundreds and millions of transactions a day, even small errors can translate into millions of dollars lost every year. But on the other hand, machine learning and AI systems are very tolerant of errors in the model because at the end they're averaged out when you're doing all of these deep learning computations. So you do a lot of averaging, and you can still achieve high accuracy because it's very probabilistic. Take an example like the picture here of Mona Lisa in this slide. Even with all the dots that are missing, you can still recognize that this is a Mona Lisa. And so you can still tell who's in the picture. So we have shown that, in fact, you can exploit reduced precision to build models with equivalent accuracy, or what we call ISO accuracy, with fewer computations. And our first paper that was published in ICML in 2015, that was kind of the first paper that was published by our digital AI accelerator team that showed that with 14 bits of precision, floating point 14 bits, you can achieve identical accuracy, the full precision example. And if you go too far, however, the models do not train with the same accuracy like with 8 bits. But you get like slow or like lower, a little bit, of degradation. And since the time, when the ICML paper in 2015 was published, internally we have discovered ways of scaling this significantly, as well as approaching this problem from a mixed precision point of view, where the calculations are divided between those that are done in high precisions and those that are done in a much lower precision. And we think that we have a path to scaling this significantly to even lower precision to be able to achieve the data points that we need to get this precision, scaling accuracy. So this is kind of the new the new Moore's law for precision scaling that we have here for deep learning. So IBM Research has been leading in reduced precision scaling while maintaining ISO accuracy. You get the same accuracy of the model as you would get with full precision. And as I mentioned, in 2015, we proposed the world's first reduced precision neural network training and started this precision scaling journey. And this has been very effective for hardware performance improvements. Every 3 years, arithmetic precision has been scaled by 2x, which improved 4 to 6x hardware performance without losing any neural network accuracy. And more recently, in 2018 and 2019 at the NeurIPS conference, the team has successfully shown world first 8-bit training and continue to lead in this precision scaling. And in inference, we also first demonstrated high accuracy results in using 2 bits and 4 bits. And more recently, we also have shown the world's first 4-bit training last year in NeurIPS 2020. And also at the ISSCC 2021 conference, which is one of the top conferences, in AI chips, IBM introduced the AI chip leading in precision scaling with 8 bits training and 4-bit inference. So this also has attracted a lot of widespread coverage and media attention. These are just some of the snapshots of how the media covered this, where it's highlighting that how we're demonstrating or showcasing energy efficient chip to power deep learning, and also the 4-bit computers, tiny 4-bit computers. They're all you need now to train AI. So this is really huge in terms of advancing state of the art and enabling training or inference for deep learning with much smaller computation. This has far-reaching implications on how do you design, efficiently these hardware and for both training and inference. And these are also some of the recent innovations in our digital AI core innovations. You can see here very recently we had the first integration of our next generation Z processor with this AI core that was built based on precision scaling. And this is shows the AI specification. This is a chip that does 6 teraflops per chip, up to 200 teraflops per system, and it is focused on low latency AI inference and can deliver exceptional performance real time. All right, so now what's the next step? As I mentioned, with reduced precision, you can continue the progress of 2x per year, but to be able to get to the next level here, the next evolution of these specialized AI hardware is really rooted at addressing the performance efficiencies loss that you get from data movement between computational units and the memory. And this is where analog comes to play. So I just want to quickly brush on some of the key concepts here for deep learning that I'm sure all of you know. In deep learning, we have these operations when we're doing training, but also when we're doing inference in the forward pass. So there is the forward pass where you do multiply, accumulate. So multiply, add, and then there is the updates, and then there is all the activation functions. So these are basically most of the computations that govern deep learning. Matrix multiplications and nonlinear activations are reoccurring operations in deep learning networks, and they're basically kind of the dominant mathematical operations that happen here and that are foundational for deep learning. So when we talk about analog AI, the concept here is using non-volatile memory or NVM technology, which enables in-memory computing, which basically eliminates this traditional Van Neumann bottleneck. And I'll talk about what I mean by this Van Neumann bottleneck in a bit. And how this is done is you map neural networks to analog hardware. And you store the neural network's weights as a property of the non-volatile memory device or material itself. And what this does, it eliminates the data movement altogether. And this AI approach can offer unparalleled speed up and energy efficiency for AI workloads. So how does this work? So let's look at how this is done conceptually. In digital accelerators today, they work typically like this. You have the processor on one side, you have the memory on the other side, and they're connected by a bus. And this is known as the traditional Van Neumann architecture. Let's say you want to multiply two numbers, A and B. So they start by sitting in memory, and then they're sent to the processor. The answer is computed in the processor and sent back to the memory. This consumes a lot of energy. Just imagine when you're doing all these computations and when you have a large models, how many numbers you have to crack here and how many things you have to send between the memory and the CPU. Analog accelerators, or what we call also in-memory compute, they work differently here. So what happens here is, in memory compute, they try to do the computations in the memory itself. And conceptually, how this is done, you get rid of this processor. And you do everything in memory by storing A in the memory and sending B as a voltage. So let's look at how this network is. And then basically the output of the computations, all this computation is done in the memory itself using the laws of physics. So let me maybe quickly show you conceptually how this is done, and especially this very key concept that we call the resistive memory product. Consider this simple circuit here, and I hope you still remember some of your foundational physics. There are here 3 wires and 2 resistors, and assume that the 2 resistors have conductances values G1 and G2. If I apply voltage V1 and then voltage V2 at these 2 wires, the first injects a current V1 times G1, and the second also injects a current I2 is V2 times G2. And this is actually a very famous law, which is the Ohm's law. And then down the line here, what happens is these currents get added, get summed together. So the resulting current is I1 plus I2, which is V1 times G1 plus V2 times G2. And this is the famous Kirchhoff law. So what we're doing here is we're relying on Ohm's law and Kirchhoff law to perform the multiplications and additions in the analog domain. And if we extend this concept further and create a dense grid of resistances which can be programmed beforehand, these G11, G12, you can program them beforehand and think of them as the weights of your neural network. And then you apply a vector of voltages inputs, V as the inputs. Then the current in each vertical line is the dot product of the input vector and the vector programmed or residence conductance as G. So the currents coming out are the result of the vector matrix multiplication. And the grid of resistances here that you see is called analog crossbar point array. So what we're seeing here, this is kind of magical. You basically just inject some current, some voltage, and then you program some resistances in this material on this crossbar array, and then this vector multiplication just happens magically here using the law of physics, and it happens instantly, in one step.
Please, Dr. Kaoutar, if you could wrap up in 2 to 3 minutes, please.
Okay,
thank
thanks.
you.
So what I showed basically just some of the key foundations for analog in-memory computing. I'm just gonna here go quickly showing how a neural network is mapped in memory, analog memory computations. And basically, so you have these crossbar arrays that you stack together, and that results in creating, you map a neural network to analog hardware, and then you can use, what we call these cross points, multiple devices like phase change memory, which can hold, you can change the resistivity of the material and the way you store the weight of the neural network. And there are many devices that you could consider for in-memory computing, and there is no ideal device. There are things like phase change memory, random access, resistive random access memory, electrochemical, and so on. So I'm just going to skip quickly here. So when we're looking at designing these analog AI hardware, we consider either inference or training. And because there are, of course, in training, there is the forward pass and the backward pass, but in inference, there's only the forward pass. So to accelerate the training of DNNs, the accelerators to need to implement the forward, backward, and update passes for computing the stochastic gradient descent. And if the accelerator is only targeting inference, you would need to program the weights ahead of time, and then you only accelerate the forward pass, which is the inference step. So that's basically, how the differences between forward inference and training, and then the way you design also the material that you need. Well, we need to have different properties depending on whether you have inference or training. And with analog in-memory computing, there are lots of advantages here. The first one is improved energy efficiency. You can see here that matrix multiplications, they consume the majority of the operations in deep learning. So accelerating this is really huge. And then you can also get zero standby power, meaning you take advantage of the non-volatile memory technology, which gives you low startup time, no need to fetch the weights from memory like what happens in digital, and very low latency. And these are all critical to enable, training these large models, and especially if you're thinking about AI at the edge. I'm going to skip here. I mean, with analog AI, there are also lots of challenges because there are things that we call noise, circuit variations, non-idealities of the material itself. And that's why a lot of algorithmic advancements and then tricks need also to be implemented to be able to counter these noises and so on, and deliver neural networks with high accuracy in analog. So given all of these, what I've done is just I've given a glimpse of the many of innovations that AI is driving in hardware. And we've recently announced, the IBM AI Hardware Acceleration Kit, which is an open source toolkit that you can all take a look at and take advantage of. And it also allows you to understand and evaluate, today's workload with these next generation platforms or AI hardware accelerators. There's also toolkit, so is as I said, an open source one, and it has many capabilities like evaluating analog for AI training, for inference, doing hardware-aware training, which is very key to make these models work well on analog hardware for inference. And it also comes with a web interface, which allows you, it's a no-code experience that allows you to interact with, these future AI hardware accelerators without having to write code. You just plug and play and then run simulations in the cloud and then get results and so on. I had a demo, but given the time, I'm going to skip it. And we're also, we're doing this by building these chips. So these are some of these, the recent achievements today, like first demonstrations of an analog AI chip. And these were showcased, at the VLSI 2021 conference. 2 chips that we have built. They're still in prototypes and hoping to share them with the community, through our, the open source or the Composer interface very soon. So building these efficient and faster AI really requires rethinking, computer architecture, rethinking system design, rethinking and going beyond exact computing using approximate computing techniques. Going beyond digital computations by looking at analog, and even going beyond classical computations by even looking at quantum for AI. So this wraps up my talk. I thank you for your attention.
Thank you very much, Dr. Kaoutar, for this interesting and insightful talk about the future of AI hardware and chips, especially that advancing AI requires high computational capabilities such as ISO accuracy and analog AI chip. Allow me to thank you once
Thank you
again.
so much, Iman, for having me, and thank you so much to the audience. All the best to all of you.
Thank you.